Right, so this is question 11. A student is investigating the density of a liquid. The student uses scales that show the mass the nearest grams, and the student uses a measuring cylinder that's marked with volume in centimeters cubed. First, the student puts an empty measuring cylinder on the scales. Then the student puts some liquid in the measuring cylinder, and for both of them it gives you the mass values. And then the student looks at the level of liquid in the measuring cylinder. Complete the results table for this investigation by transferring the information given from the opposite page. Well, if we go back to the previous page, you can see that the student puts some liquid into the measuring cylinder. So this is going to be the mass of the measuring cylinder and the liquid. Okay, so 325 grams. Always need to include units. It then needs the mass of the empty measuring cylinder. Again, we go back to the previous page, while the empty measuring cylinder has its mass here, and that's 106 grams. So we put that into the table. And then we've got to give the mass of the liquid in the cylinder. Well, we know that the measuring cylinder and the liquid is 325. The cylinder is 106, so if we take one away from the other, then that's going to give us the mass of just the water alone, which is 219 grams. And then we need to know the volume of the liquid. Now the diagram here is not particularly clear, but we're looking at the level of the water along here. Now the scale is going up in two, so we've got each of the big 150, 160, 170, and then although the diagram's not very good, I think we've got another 3 divisions above that. If each one is 2, then that should be 176 milliliters. So let's put that into the table. And then next part, show how the student could use these results to calculate the density of the liquid. We're using this equation here where density is mass over volume. What we've got to be clear of though is that what we're putting in here is the mass of the liquid. Now if you were to actually do the sum, then we'd be doing 219 grams divided by 176 milliliters. You can see here that your units are going to come out as grams per milliliter. Part C asks for you to give 2 ways in which a student could improve the investigation for a more accurate value. Now accuracy means how close your value is to the actual value. So how can we make it more likely that our density value is the actual value which you would find if you were to look it up on the internet or in a book? Well, one thing you could do is you could check that the electronic balance of the scales reads 0 grams before anything's placed on them, because obviously if it doesn't, then that's what we call a 0 error, which is going to affect all of our results. Another thing you can do is to use a large volume of water, and the reason why this can help to give you a more accurate result is when you measure anything, there's always some kind of error. So when you measure using the electronic balance in this case, then we've always got an error of plus or minus 1 gram. When we use the measuring cylinder, we've got an error of plus or minus 1 milliliter. Or sorry, 2 milliliters, I think, looking at the scale, although we could go to 1 halfway between the divisions. Now, we have to bear in mind that any result we take will have an error, but we can reduce the effect of that error and reduce the percentage of the final value if we use a large volume. So for example, if we only used 20 milliliters, well, plus or minus, say, 1 milliliter, that's still 5% of the final value. If we chose to use 100 milliliters, then the 1 milliliter error is only 1%. So the bigger the numbers we use, the smaller the error is as a percentage of our value, and that's likely to make our results more accurate. Question 12 is about the 2 cups of coffee. They're the same size. One cup is full, the other is half full. And we've got to compare the pressure in the coffee at the bottom of each cup. Now, the most obvious thing then is to say that the pressure is going to be highest at the bottom of the full cup, or the opposite argument, that it's going to be lowest at the bottom of the half full cup. Now the reason for that is that we've got a higher mass of liquid above it in the full cup, and so you've got a bigger weight of water acting downwards. Now hopefully you can remember this equation. The change in pressure as you go down and under the surface of a liquid is equal to the change in height times the density of the liquid. Okay, that's the symbol here, rho, times g, which is the gravitational field strength. So the bigger the height, or the bigger the depth really that you go to under the water, the greater the change in pressure. So the deeper you go, the higher the pressure change. Now in this equation, the density and the gravitational field strength will stay constant for both cups. The only thing that's going to change is going to be our depth, or our change in height. So if the change in height or change in depth increases, then the pressure change is going to be biggest. So as you go deeper into the liquid, you have the highest. Now question 13 is a radioactivity question, looking at radioactivity to treat tumours, so radiotherapy. So a horse has a tumour near one eye. The tumour is several centimetres across. A vet treats the tumour using radiotherapy, and the vet puts an isotope called iridium-192 into the tumour, and this emits beta particles. Okay. So we're then asked about the iridium-192 nucleus and how many protons does it contain. Well, we've got two numbers here. Okay, this is my mass number, and that's equal to the number of protons plus the number of neutrons. And then we've got our atomic number, which is simply equal to the number of protons. So how many protons does it contain? 77. How many neutrons does it contain? Well, we have to take the mass number, which is the number of neutrons and protons, and minus the number of protons, and that's going to leave us 115. Iridium-191 is a different isotope of iridium. What are isotopes? Well, you can see we've got a change in number here, 192, 191. So that gives you a big clue there that obviously the mass number has changed. So one thing we can write about them is that they have different mass numbers. But what they have that's the same, well, they have the same number of protons. Now alternatively, to write in different mass numbers, we could say they have a different number of neutrons, and alternatively to write in the same number of protons, we could say the same atomic number. Now as it was stated earlier, iridium-192 decays by beta decay. So beta particle is basically a fast moving electron, so it has pretty much zero mass and a charge of -1. Now we've got to complete the nuclear equation to show how beta decay changes the nuclear structure of iridium. Well, the first thing, it has zero mass, or close to zero mass. Now that means that we can say that the mass of the nucleus remains unchanged. But with the emission of an electron from the nucleus, it actually causes an increase in the atomic number of 1. And so our atomic number goes up to 78. So beta decay then affects the structure of the nucleus in that way. So the mass is unchanged, but the atomic number will go up by 1. Part D. The tumour in the horse is several centimetres across. Explain why beta radiation is more suitable than alpha or gamma for this treatment. Well, let's consider them all separately. Alpha, gamma and beta. Okay, so why is alpha not suitable? Well, with alpha radiation, our issue is that it is weak penetrating power. Okay, and that it cannot penetrate into the tumour. Okay, so it's not going to destroy any of the cancer cells that are there. Okay, equally you could look at the other way, that it has a low ionizing ability. Sorry, it has a high ionizing ability, and therefore it will have ionized the air and anything else that lies between the source and the tumour, and therefore it won't penetrate as far. Now gamma is the opposite. Gamma has a high penetrating power. Sorry, let's get rid of that. It has a high penetrating power, and it will penetrate all the way through the tumour, and therefore there'll be no ionization of tumour, because it needs to be a very dense material like lead or concrete in order to cause a lot of ionization. So it's going to pass through the tumour without ionizing, and therefore without destroying the cancer cells that we want to get rid of. Now beta will penetrate into the tumour, but still cause some ionization, and that's what we want. Now the energy from the beta radiation is expected to destroy the cells in the tumour over a period of several weeks. The most suitable half-life for the radioactive source would be, well, 75 minutes and 75 hours are not going to be suitable. Okay, the reason being that over time the activity is going to get lower, that is, the number of decays that occur per second, and if you've got half-lives as short as that, then within not that many minutes or not that many hours, you're going to find that the activity is so low that it's not really doing anything useful anymore. Okay, so we're going to go for 75 days. Okay, if we went for too many, 75 years, then okay, it would be reasonably useful, and we could use the radiation to kill the tumour, and the activity wouldn't get any lower over time. But then we've got the problem later on of what we're going to do with this radioactive source. Once we've removed it and we're no longer using it to treat a patient with, and we've still got to dispose of it in some way, and it's going to be radioactive for a long time. So in explaining my choice, my first answer would be A and B would need to be replaced over the period of treatment. So obviously that's not ideal, so that's one reason for choosing C above it. Now the radioactive source would have to be removed from the horse anyway after a period of time. So I wouldn't say that 75 years is completely unsuitable for it, but the problem then is that we have got something that's going to remain radioactive for a long time afterward. So D remains radioactive for a long period after treatment, which again is not what we're after. Right, the next question, last one, is about the Geiger-Marsden experiment, or the Rutherford experiment. An alpha particle is formed from four smaller particles. The diagram represents an alpha particle, and you've got to complete it. Well, hopefully you're aware that an alpha particle is a helium nuclei, and a helium nucleus is made up of 2 protons, so it doesn't really matter which one we choose here. I'm going to call these 2 protons, and the other 2 are going to be neutrons. So Geiger and Marsden aimed alpha particles at the gold foil, and most of them travelled straight through, but some were deflected as shown in a diagram. Now the scientists moved all the air from the apparatus. Why? Well, firstly, we don't want the alpha particles to collide with the air molecules, and if the tube was filled with air, then the alpha particles wouldn't get very far, because we know that they're very easily absorbed. So within a couple of centimetres they've been absorbed, and they wouldn't even go on to hit the gold foil. And describe the force that causes some alpha particles to deflect. Well, we're looking at the positively charged alpha particle coming close to the positive nucleus of the gold atoms. Okay, and that repulsion is due to the electrostatic. So we've got electrostatic repulsion between 2 like charges. So 2 positives will repel, or 2 negatives will repel. Now this experiment is famous because it proves the nuclear model of the atom. An experiment showed most of the alpha particles went straight through the foil. Some were deflected through a small angle, but a few were deflected back towards the source. So scientists concluded each gold atom had a small, dense, positively charged nucleus. Explain how the results experiment led the scientists to this conclusion. Now most of the atom is just empty space, so the majority of alpha particles are just going to go through undeflected. Some alpha particles are going to go close enough that they get some small deflect. A few will hit the nucleus straight on and deflect through very big angles. In terms of how the 5 marks are given, the mark scheme's quite useful here to have a look at. We're looking at, well, basically the following points there.